Okay, so let's start for today. So before I move on to the new content, so I want to spend a couple minutes to do a quick review on the content from the last time. Okay, so last time I considered two different things actually. So the first thing I consider is that I'm considering a rotating vector. Right, so this A vector, so just look at the figure on the left, right? So this A vector over here, and then the angular velocity of this A vector is represented by this black omega vector, right? So the direction of the omega vector represents the rotation axis, and then the magnitude of the omega vector represents the angular speed. Right, so then you just imagine that this A vector is just doing a motion like this, right? And then the second thing that I consider is the rotation of the coordinate system itself, right? So in the first case that I consider, I didn't really talk about coordinate system at all, right? It's just a vector, so you can express it in any basis that you want, but I didn't really talk about coordinate system, right? So, but then in the second thing I talked about last time is actually the rotation of the coordinate system itself, right? So the rotation of a coordinate system so means rotations of the basis vector, right? So you can see that in this figure. So I have the two set of basis vectors, right? So the black set, right, so x hat, y hat, z hat, which are fixed, and then the rotating set, which is the x hat prime, y hat prime, z hat prime. And in this picture, so I consider that the rotation, the angular velocity again is along the z axis, so that you can see that the x hat prime and the y hat prime are just going along this circle. Okay, so on the xy plane. Okay. So in these two cases, so I derive the expression for the time derivative of the vector. So in this case, right, so the dA dt is given by omega cross A, right? So and then in this case, right, so I have this d x hat prime dt equals omega cross x hat prime, right? And the same thing for the other two basis vectors. So one reminder again, so I think I've told you last time is that in both situations, okay, so the only time dependence of the vectors or the basis vectors are due to the rotations that we impose, right? So because we want this A vector to rotate like this, right? So just imagine if we don't impose these rotations, okay, so the A vector itself is just a time independent vector, right? So same thing here. If we don't impose the rotation for the basis, then this, just imagine that this x prime hat, y prime hat, and this z prime hat, they are all just constant vectors. So as a function of time, so they don't depend on time. So the only time dependence of these two cases comes from the rotations that we want them to do. Okay. So, but then towards the end of the last lecture, so I wanted to consider the following. Okay, so this time I do have a vector. So now I'm just going to draw the vector. Okay, so in this picture. So and again, I'm just calling this A, right? So but this time you could imagine that you can either express A using the basis of the fixed frame or the basis of the rotating frame, right? So you have two choices. Okay. Now we are going to consider is that now this A by itself has its own time dependence, right? So that is even you just use the fixed coordinate system. Okay, so I'm going to consider the situation that in general dA dt is not 0. Okay. So even we are not talking about the rotation of the coordinate system. Okay. And then what we are trying to do and what we'll continue to do today is that I want to find a relation between dA dt with this subscript fixed versus, so I'll explain what the subscript means, right? So versus the dA dt with the subscript rotate. Okay. So on the left-hand side, so it means that the rate of change of this vector with respect to time. So if you are an observer that is standing at the fixed frame, right? So that's what it means. And this one means that if you are an observer that is rotating with this rotating frame, then what you see, what you observe for the change of the A vector over time. So this is what it means for this dA dt with the subscript rotate. Okay. So we are trying to find a relation between these two. And as I said, right, so because now A by itself has the time dependence, okay, so it won't be just simple as this one. Okay. So last time, so I just finished this slide, right? So taking derivatives, right? So if you are going to use the fixed frame, right? So with this basis, then things should be easy, right? So the dA dt is just taking the derivative for the coefficient function. So in front of these three unit vectors, right? So that's it. But now, if you are using the basis vector of the rotating frame, so which is here, then when you take the derivative, you need to be careful because now the basis vectors themselves are not constant over time also, right? So therefore, when you take the derivative, not only that you need to take the derivative for the coefficient functions, you also need to take the derivative for the unit vectors themselves, right? So therefore, if you use product rule, right, so you get 6 terms, and then I group the 6 terms into these 2 groups, right? So the first one is just the derivative for the coefficient function, and then the second group is the derivative for the basis vectors themselves. Okay. So the first group, so I'll call this, right? So dA dt with the subscript rotate, right? So I hope you understand why. It's because if you are an observer that is rotating with the rotating frame, then from your viewpoint, you will think that these 3 basis vectors are just constant to you because you're rotating with them, right? So then the only time varying things that you see will be due to, right? So the time derivative of the coefficient function. Okay. So, and now this is what I have, but then the second term, right? So we'll take care of the fact that, in fact, all these 3 basis vectors are rotating as a function of time. Okay. So then I'm just going to write down the same equation here one more time, right? So and then so one more thing, remember. So in this case, just for simplicity, so you for you to easier to imagine that, then you see that the rotation axis is along the z-axis. Right. So, but in general, so when I'm writing out the formula, I did not really assume that. Right. So the omega can be any vector pointing in any direction. Okay. Okay. So then this dx dt, dx prime dt, and so on. Right. So can be written as, right. So omega cross x prime and so on. Right. So as we have derived from last time. Okay. Sorry. This should be hat symbol. Okay. Okay. So now the again this omega cross can be treated as common factor. That I'm just going to take them out here as a common factor. So then this vector is just the A vector itself, right? So although this is expressed as in the rotating basis, but it doesn't matter, right? So you know that this, but no matter what kind of basis that you are using, this one is just the A vector anyway. So then finally, so I have this dA dt rotate plus omega cross A. Okay. So then I'm going to write the left-hand side as dA dt fixed. Okay. So I add this subscript fixed. Okay, just to remind ourselves that this is different from this. Okay, so these two are different. Okay, so now if you recall, right? So recall what we had again from the last time, right? So just consider one more time the situation of this, right? So in this case, right? So if A by itself does not have any time dependence except the fact that this is rotating like this, right? So then you have this dA dt just simply given by omega cross A, right? So now that if A has other time dependence, okay, and now the dA dt in general can be written like this. Okay. In the case we had from the last lecture, right? So this is just 0. So that's why we have this dA dt just given by omega cross A. Okay. Then in general, we have this. So one remark here is that the second term on the right does not come with any subscript. So I did not write the subscript, rotate, or fix, right? So, and in fact, it doesn't matter whether you express this second term here using the basis of the fixed frame or the basis of the rotating frame. It doesn't matter. Omega cross A is omega cross A. Okay. And in fact, if you think a bit more, omega vector itself is quite special, right? So if you go back to this picture, right? So omega vector would be a vector pointing like this, right? And so you understand that we are just considering the case where the angular speed is always just a constant, and then the direction of the rotation axis never change, right? So then that's what I have here. So you can see that no matter you use the fixed frame or the rotating frame, so omega vector would be a constant vector anyway, right? Doesn't matter which frame you use. So omega vector is kind of special, right? So even you pick another rotation axis, right? So no matter what frame you use, so omega, the constant vector. Okay, so here, okay, so I want to remind you one more time. Okay, so then, right, so dA dt with the subscript fixed means that you are going to express the vector in the fixed basis and then take the derivative of the coefficient function. Okay. And whenever you see the derivative with the rotate subscript, then that means you express the vectors in the rotating basis and then take the derivative for the coefficient function. So it's very important to be clear about these two, because what we are going to do next is that we are going to take the time derivative one more time. And then you actually see that, as you'll see in the next slide, is that what if you take the first derivative with the subscript fixed, but then the second derivative using the subscript rotate. So that is what if you have something like this. So you see the subscript comes together. Okay, so that at that part that might start to be a bit confusing. So that's why at this point we all have to be clear about what the subscript means. Okay, so now what we really care about is to express the velocity and the accelerations of a particle. Okay, so in the frames. Okay, so this A can be any vector, so any physical quantity. Okay, so specifically, we care about the velocity vector and the acceleration vector. Okay, so then first, I would like to express the velocity of a particle in the fixed frame. Okay, and find how it is related to the velocity of the same particle in the rotating frame. Okay. Then to do that, I'm going to just put A equals R. Okay, so the R is the position vector of a particle. Okay, so the particle by itself can be accelerating, doing different kind of motions. Okay, so due to external forces. So that is what I have. It's just the following. Okay, so just dr dt over here, right? So dr dt here, and then dr dt here. Sorry, r here. So this is what I'm doing over here. And then this dr dt with the subscript fixed, I call this v fixed. Okay, and then this dr dt with the subscript rotate, I call this v rotate. So therefore, right, so the velocity of the particle observed in the fixed frame and the velocity of the same particle observed in the rotating frame is related by this equation here. Okay. So then what I need to do next is to find the acceleration, the relation of the acceleration. Right? So that is, I need to take the derivative one more time. Okay. So I'm going to find the so-called A fixed, where acceleration observed in the fixed frame, right? So that would be, by definition, is this one. Is that I have the d, is that the dv fixed dt. Okay, so with the subscript fixed. And it also means that, first of all, I have this r vector expressed in the fixed frame, and then take the derivative. Okay, so after taking the derivative, take the derivative one more time. So that's what it means. Okay. Then on the other hand, this is the definition of the A rotate. Okay. So that is, you have a velocity in the rotating frame, and then you take the derivative one more time, okay, in the rotating frame. So how do I get to this, right? So I'm going to just need to take the time derivative of this one more time, right? So what I'm going to do, right? So okay, instead of if I just take the derivative of these both sides one more time, so you need to worry about the bases also, right? So the different bases. So what I'm actually going to do is to make use of this equation one more time. Okay. So instead of putting A as R, what I'm going to do is that I'm simply going to put A as the Vx. Okay. V fixed. Okay. Like this. Then this is the equation I got. Okay. So the physical meaning of the left-hand side is clear. Okay, so that is exactly the acceleration observed in the fixed frame. But then what we need to be extra careful is the right-hand side. It looks messy, and the interpretation is not clear yet, right? So because now you can see that I have this subscript mixing. Okay, so subscript fixed, and then the subscript rotate. So need to be very careful about the terms over here. So at the end of the day, we want everything on the right-hand side to only have the subscript rotate. Okay, so because I want to find a relation between what happened, what is observed in the fixed frame and what is observed in the rotating frame. Okay. Then okay, so then how do I deal with this? Okay. So remember, I told you that, right? So when I write down this time derivative with the subscript rotate, so that means the first thing I need to do is to express this vector that is to be differentiated in terms of the basis of the rotating frame. Right. So just recall these two definitions here. Right. So when I take the derivative with the subscript rotate, so that means I have to first of all express this A vector using the rotating frame basis. But clearly, this V fixed is not expressed in terms of the rotating basis, right? So the V fixed itself is expressed in terms of the fixed basis. So therefore, I'm going to first express this one using the rotating basis. And how do I do that? Again, use this relation here. Okay. Right, so remember this. So this is in the fixed basis. This on the right-hand side can be in the rotating basis. So therefore, this V fixed replaced by this. Okay. And then this v fixed, I also replace it by this. Right. So at the end of the day, as I said, everything on the right hand side want it to be the rotating basis. Okay, so now if you understand how to get to this step, how to get from this step to this step, then you are good. Then the next step is just that you're just taking derivatives. You are actually ready to take derivatives. Right. So this one you just break it down into two terms like this. Okay. So then the first term here, now you see what we want is that the dv rotate dt with the subscript rotate. Right. So the first term is the acceleration observed in the rotating frame. And then the second term here, and the third term here. So the second term here, we can further simplify by just taking this omega cross, right? So in front of the derivative symbols, because omega itself is a constant, so that's why it can be taken out like this. Okay, so therefore this the last term I didn't do anything. Now you can also see that this dr dt with the subscript rotate, that is exactly v rotate. Right, so that is exactly just v rotate. So then I have this omega cross v rotate, and I also have this omega cross v rotate here. So they can be added together. So therefore, at the end, so I have this 2 times omega cross v rotate. And then this plus omega cross out. So again, here you can see that I don't have any subscript. Okay. So you are free to express the last term, okay, in the fixed frame or in the rotating frame. Okay, then both are okay in principle. So then this is the result we want. We relate the acceleration of the particle in the 2 frames. Okay, so now if you are still a bit confused by these 2 different subscript comes together, so in the appendix I have another slightly different way of presenting this derivation. Okay, I'll just also quickly go through that. So with that writing style, then you don't really need the subscript, and it might be for some of you, you might find it a bit more comfortable maybe. So what I do here is that I'm going to start from this result here. Okay. So I want to relate the second order derivative of the vectors. Okay, so in the 2 frames. So I'm going to start from this result. So dA dt equals to this whole thing. And then I'm going to take the derivative on both sides one more time. Okay, so therefore, so if you understand the previous slides, then this slide you can just ignore. Okay, but this is just another way of writing things out. So as I said, right, so derivative for both sides. So d squared a dt squared equals this whole thing. So remember, so d squared a dt squared would be the second order derivative of the a vector in the fixed frame. Right, so this is understood. Right, so this one. So now look at the right hand side. So I have quite many terms to deal with, but that's actually not that complicated. So if you just consider the derivative of this first group, what you would get? What you would get is this term and well, this group of terms and this group of terms without the factor of 2. Okay. So if you just take the derivative of this first group, and if you just take the derivative for this second group, what you get again would be this group and this group. Okay, without a factor of 2. So therefore, if you have taken the derivative for the whole thing, then you have to add these two terms plus these two terms. So that's why you get an extra factor of 2 over here. Okay. So like this. Okay, so no other tricks, just product rule. So now I have this d dt term. Okay. And then I'm going to, again, use these 3 formulas to get rid of d dt terms. So then you can see that this d dt terms just becomes the omega cross term. Okay, like this. So now I just take this omega cross as the common factor. Then you can see this omega cross, this whole thing here. And then there's the last group also. I take the omega cross out of the derivative sign and then out of the whole bracket. So this. So now you still see I have 3 derivative terms here. Again, I want to get rid of them by using the same formula one more time. Okay, so that's why this d dt term also becomes this omega cross term. Okay. So now this omega cross term can be taken out again. Then I have these 3 terms like this. So you can see that this is the term with the second order derivative. This is the omega cross term, and this is the omega cross term. Okay. So now this one is exactly the second order derivative of this vector A in the rotating frame. Right. And this is exactly the 2 omega cross dA dt term in the rotating frame. And finally, this is omega cross A. Okay, so this is just a slightly different representations. Okay, so of the derivation. Okay. Okay, so now I have these relations. Okay, so between the two, the acceleration in 2 frames. Then let's go back to let's talk about the fictitious force. Okay. So again, right? So in the fixed frame, so we know that F equals ma, right? So F equals ma fixed, right? So it's in the fixed frame, then no problem with this. So however, right? So you understand that in the rotating frame, which is a non-inertial frame, so you cannot simply write down this. Right? This would be wrong. Okay. So however, just like the last part of the chapter, we are trying to write something like this, is that I'm going to have some kind of terms together that I call F effective, that is equals to ma rotate. Then what I need to do, right? So then I can again start from this F equals ma fixed, and then this a fixed is equals to this whole bunch of terms, right? So F equals to this, all this, and then I'm going to put all the terms on the to the left hand side except the ma rotate term, right? So then I have this m minus this whole thing equals ma rotate, right? So then this whole thing would be what I call the F effective, right? And F effective would be composed of, right? So the F real, which is obviously this term, right? So plus the F fictitious, that is the everything in red, right? With the minus sign. So therefore, right? So the fictitious force is given by minus m omega cross v minus m omega cross r. Okay. So, and this is just a diagram that show you the directions of different vectors. Okay. So the first term here is called the Coriolis force, and the second term is called the centrifugal force. So I believe you might have heard of the second term, okay, but might not be the first term, right? So the centrifugal force. So centripetal you have heard of, and I believe you also heard of centrifugal force, right? It's a pseudo force, it's not a real force. So because if you look at this, for example, this particle doing this circular motion like this, right? So the minus omega cross r will be a force that is pointing away from the rotation center, right? So that's the centrifugal force. So I think, as I said, you might have heard of a centrifugal force, and I believe that is the one that is quite intuitive, right? So it's quite easy to understand, right? So because you might have some related kind of the daily life experience, right? So just like if you sitting on a car, sitting in a car, and then if this car is doing a circular motion like this, right? So it's kind of turning to the right, then somehow you feel yourself having the tendency to go to the left, right? So that's the centrifugal force. Okay. So then this one no problem, but then what is the less intuitive would be the Coriolis force. Okay. So if you look at the direction, if you look at the direction of the Coriolis force, okay, so what does it look like? So what is the direction of the Coriolis force? So it's omega cross v rotate, right? So actually, let me remind you of another thing that is not related to what we talk about here, but I just want to remind you that you have actually learned about a kind of force that is related to the cross product. Okay, so you still remember the Lorentz force law? You still remember this, right? So just suppose you have a region of uniform magnetic field, right? Let's say you have a region of the uniform magnetic field, right? So this magnetic field is like pointing out of the page, right? So and then if you have this particle moving like this initially, right? So then you do QV cross B, right? So then you know that the force is actually pointing this way, right? So you use your right-hand grid rule, right? And you might still remember that then in this case, then the particle will just perform circular motion. Okay. So now if we think of Coriolis force, right? So it's also mathematically the formula is very similar, right? So omega. So instead of minus 2m omega cross v rotate. So that is, I can also. So that is minus omega cross v rotate. So that is v rotate cross omega. So it could be, let me just write it this way. Like this. Right. So mathematically, the same. I'm not saying that the physical origin related. Okay. But so in this case, you could imagine that. So in the rotating frame, so suppose if you again consider a particle moving in the rotating frame initially like this, right? So and then suppose your omega vector is pointing out of the page, right? So just like the direction of the B field, then you could imagine that, right? So that is to say the direction of the Coriolis force is also always perpendicular to the velocity of the particle, right? So in the rotating frame. Right. So then here then how you have kind of a sense of how this Coriolis force will behave, right? So it's always just perpendicular, right? So to the direction of your velocity. Okay. So, but however, when we think of the fictitious forces, we can't really just consider them separately in principle, right? So because you understand that the two terms come together, right? So you cannot say that you just consider one of them, right? So therefore, for the magnetic field problem, right? So if you just have the magnetic field, then you understand that the trajectory is just a simple circle, right? So but for the case where we deal with this situation, so at the end, right? So we may not just have a simple circular motion, right? So because the circular motion, okay, so can be obtained due to this Coriolis force term, but what about the combined effect with the centrifugal force, right? So you always have to put them together, okay, so in order to see the final effect. Okay, so but before we take a break, so I'll just show you a video here to illustrate the Coriolis effect. Okay, so the setup is this in the video, it's just like this. So this is a rotating platform. So just imagine that the kind of rotating platform that you can see in children's playground, and then if you just both you have two or more people sitting on this platform. So basically, they are all in the rotating in the rotating frame, right? So and then they are going to try to set up some motion. Okay, so to see what happens. Okay, so this is the setup here. Okay, so I don't know if you can hear the voice.
With a simple game of catch, I think I've found a way to show an effect that will have you doubting your very own eyes. Now, they don't know it yet, but our budding ball players sitting on our specially rigged merry-go-round are about to demonstrate a rather astonishing optical illusion. Here's the game, right? You're going to throw the ball straight to what's your name, Victor, right? But this time, I'm going to complicate things slightly. I'm going to rotate the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough,
yeah,
like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it. All right.
Yeah.
Right. So initially, if this rotating platform is not rotating, right? So if we try to throw a ball in straight line, then the one opposite to her can catch the ball, right? No problem, right? So but what if now they try to make this whole thing rotate, and then and they try to do the same thing, they try to throw the ball to the person opposite to him or her, right? So and see what happens.
Right, what's going to happen, dude?
It's going to veer off to the left.
So the ball is going to swerve off to the left.
Yep.
And you might catch it.
Possibly.
Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me, and I'm going to catch it like the champion that I am.
Show me the catch. Okay, great. Right, okay, so everyone, no, hang on, one more. Spencer,
He's not arrogant.
just quietly
He's
confident.
not catching it. He's
Really?
not catching it. No,
So what's going to happen to the ball?
I'm catching it. It's right here.
Great. So we've got one saying to go off to you, one saying to come to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round, but where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left or by the person to the thrower's right? Right, in your own time, throw the ball.
I got this. Oh,
Whoa. So the answer was D. It was caught by the person on the thrower's right. Our camera angles seem to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw? Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills.
That's right.
yeah, it did. It just curved right over this way.
So let me get this straight. So you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah, I threw a perfect throw.
What did you see?
Yeah, curved right in.
Right, so we're all agreeing here the ball curved in midair.
Yeah.
Yeah.
And you didn't cheat this at all.
No, I didn't.
Okay. And do you know why it did that?
No.
No.
No idea. It's called the Coriolis effect. And it's very simple. It's objects in motion appearing to be, it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight, still going straight, but the table is moving below you. And all of a sudden, look who's in front of that straight moving ball. And it looks like it's bent off to the right because you're still looking at the guy you were intending to throw it to. And that, ladies and gentlemen, is the Coriolis effect.
Okay, so that's it for the video, and so after the break, so I'll actually just try to say more. Okay, so based on this rotating platform setup. Okay, so I think so. Let's get a 10 minutes break. We'll come back at 12:30. Okay, so in this part 3, I'll specifically talk about this centrifugal force and Coriolis force. Okay, so this quote unquote for the force, because as I said, so these are fictitious forces. Okay, so not real forces. So the example that I'm going to use is the same as what you have seen in the video that I show you. Okay, it's a rotating platform. Okay, so or the so-called merry-go-round. Now I'm going to again just consider this the observer is just a camera. Okay, so mounted. Okay, so at the top somewhere here maybe. Okay, so the camera, which is the observer, is just always rotating at the same speed as the rotating platform. Okay. So we are just considering some experiments that we can do in this rotating platform. Okay. So first of all, I have following assumptions for this platform. Okay. So I'm just assuming that this angular velocity of this rotating platform is constant given by this omega. Okay, so it's just controlled externally. Okay, so such that the omega is always fixed. It doesn't matter what is happening. Okay, so on the platform. Okay. And then for the surface of the platform, okay, so sometimes I assume that this is frictionless, so completely smooth, but sometimes I assume that it has friction. Okay, so I'll specify that. Okay. So the first case I want to consider is that there's a small mass on this rotating platform, and this mass is at rest observed in the inertial frame. So what does that mean? So that means that I just put this mass on this completely smooth platform, right? So and it is initially if it is at rest, and now if you start making the platform to rotate, this one won't follow, right? So because if there's no any friction, right? So then what happens is that if you are in the inertial frame, that is if you are just standing next to the platform but not rotating, then you just see that the mass is not moving the whole time, right? So just like if you look from the top, it will be something like this. So just this green dot here, it's just the position of this mass here. So but in the rotating frame, right? So what happened if you in the rotating frame, you actually see that the mass is going along this red line like this. Okay, so you see that this mass is going like this. Okay. So because the mass is, you understand why the mass is not moving, but then the camera itself is rotating. So that's why it looks like this. Okay. So then if I want to consider the rotating frame, right? So and then now if I want to just explain this kind of motion, or so-called motion, right? So in fact it does not move if you observe from the inertial frame, but in the rotating frame it is indeed doing this circular motion, right? So I want to explain this, right? So by using the fictitious force, right? So what do I have here? So first of all, in this rotating frame, so in both inertial frame and rotating frame, we'll say that there's no any real force, right? So because the friction is 0, right? So the gravity is in the vertical direction. That's not relevant. That's I don't say that I don't include that in the real force, right? So I just consider the force along the plane. Okay. So therefore, right? So in the rotating frame, I'll say that the real force is 0. Okay. So what about the Coriolis force? Right. So the Coriolis force. So again, let me copy the formula one more time. Okay. So I have the two terms, right? So the Coriolis force is minus 2m omega cross v. So this v is understood that this is okay. So let me just write it in the rotating frame, right? And that this centrifugal force is given by this. Right, like this. So initially, right? So initially, let's say, right? So you understand that initially it has a velocity that like this, right? So this is the v rotate. Then the Coriolis force. So what is the direction, right? So the omega, right? So you know that the omega is pointing up like this, right? So that means here the omega is pointing out of the page, right? So then you understand that so what is omega? What is the direction of the omega cross v rotate, right? So you use your right hand grid rule, right? So you have this omega cross minus omega cross v. You find that this is pointing towards O, the rotation center, right? And the magnitude, right? So the magnitude of this v rotate, right? So you know that this is just equals to r times omega, right? So because if this is not moving, and if this thing is rotating, then apparently, right, so the linear velocity of this mass in the rotating frame is just r times omega. So therefore, the Coriolis force is 2m omega times r times omega, which is pointing towards O. Okay. So then that is, I have this. So 2m r omega squared. So what about the centrifugal force? Right, so if you do omega cross r, right? So again, you remember that. So this is that one. You know that it must be pointing just from your common sense, right? So you know that it's pointing away from the rotation center, right? So and the magnitude is mr omega squared, which is the half of the Coriolis force, right? Then the net fictitious force would be this one minus this one, and which is just mr omega squared pointing towards O, right? So this amount pointing towards O, right? So give me the exact amount of the centripetal force that we need for this to perform a circular motion. Okay. So that makes sense. Okay. So now the second experiment is that this time I'm going to give this mass some initial velocity v0. Okay, so towards the center. So just like what you see in the video, right? So someone is throwing a ball, right? So from this side to the opposite side, right? Just like that situation. So now, if we are in the inertial frame, so we'll just say that, okay, so this mass is just moving on a straight line and then get across the entire platform. Okay. So in the rotating frame, however, you see that the trajectory of this mass goes like this curve. Right. That's what you have seen in the video. Right? It looks like this. Okay. So now do we explain that? Then again, we're going to consider, right? So the fictitious force acted on this mass, right? So initially, so if it goes like this, then you understand that the as I explained before already, right? So this is always the Coriolis force is always perpendicular, right? So to the motion, right? So that is the Coriolis force will always be pointing like this, right? So it depends on the velocity of your particle. It's always pointing like this, the Coriolis force. Something like that. So now, what about the centrifugal force? Okay. So the centrifugal force will always be away from the center of rotation, right? So the centrifugal force will always be like something like this, right? So it's not very accurate drawing, but you understand this is always something away from O. Okay. So and now combining these two forces, actually, at the end, this curve is not just as simple as a circular arc. It's actually would be more complicated than that, because if you have just a circular motion, right? So you need you know what you need, right? So you need a force that is always pointing right perpendicular to your direction, your velocity, right? So but now I have two forces, okay, so playing their role together. So therefore, this is not just a circular arc. Okay. So here I draw a few pictures. Okay, so is that if I consider different cases where I have different magnitude of the V naught, okay, so then the trajectory you see would be different. Okay. So if it is, so this is the case that I just show you in this slide. Okay. And if you decrease the magnitude of V naught, okay, you see that the bending is more significant. Okay. So does it make sense though? Okay. So if you think about the inertia frame, then things would make sense, right? So because you could imagine that again, let's go back to the video, right? So just like throwing the ball and then catching the ball, right? So if you have a very slow angular slow V naught, then what happened is that, right? So I have a person here. Let's say you have a person here, and then you throw out the ball, and then what happened is that you will keep moving like this, right? So as a function of time. So if V naught is small enough, right? So that is this ball is moving very slowly. Then that means you might have enough time. Okay, so for you to travel from here all the way to here and then catch the ball. So then that would be exactly this case, right? So throwing this out at the end, catch it again by yourself, right? So that is you throw it and then you have traveled for half a circle and then you catch it by yourself. Right. So now however, if V naught is higher, then maybe when you travel up to here, the ball already reached the other side, then you cannot catch it. Right. So that would be this case or this case. Right. So you can actually think of more extreme cases, right? So if you throw it even slower than this case, okay, so then what would happen? Okay. So I'll get to that, but let's consider two more cases. Okay, so this time I'm not trying to throw this directly towards the center, right? So but I try to like give an initial velocity with an angle like this. Okay. Then what I end up having is a trajectory looks like this. Okay. And if I have the velocity to this side, then the trajectory that I end up getting like this. So, but no matter what, whenever you do this omega cross V, right? So minus omega cross V, you'll find that the bending is always towards your right hand side. right? So it's always towards your right-hand side. Okay. So the amount of bending may be different, always towards your right-hand side. So, but now if you look at the formula, right? So again, the minus, right? So 2m omega cross v, right? So then you might ask, so if I just look at this, and if v is small, then that means this whole term, the magnitude should be small. That means the force that make you to bend should be small. But then why do I get a more serious bending? So, but why is that? Right. So omega, right? So omega is fixed, right? So v getting smaller, you should get a smaller force. So why the bending is more significant? Right. So because the magnitude of the force is not the only factor, right? So the other factor is how fast you move, right? So just like if you have a very large initial velocity and versus very, very small initial velocity, right? So even if I apply the same force to bend your trajectory, so you understand that the bending will be different, right? So if I apply the same force to bend your trajectory, so this one, right? So the bending will be more significant than this one. So therefore, right? So although the force is smaller, but because the velocity is smaller, that's why the bending, okay, so at the end will looks more significant. Okay. So on the blackboard, I just for fun, okay, so you can try to actually run this small, very simple MATLAB program to generate some trajectory by yourself. Okay, so it's just that. So just on Blackboard, you can download that if you want. If you can set up your own initial velocity. Okay, so you can choose the x component of the initial velocity and the y component of the initial velocity, and then it will just generate the trajectories for you. Okay. So, and you can see that if you, okay, so this case showing that if you really have a very, very small initial velocity, okay, so this would be the very funny looking trajectory that you get. So this is the case where the velocity is even smaller than this. So what you can imagine what happened is that if you throw the ball at a very small velocity, you might do, even you arrive here, the ball has still not arrived. You might do a few more round trip, okay, so before you catch the ball. Right, so that's how it ends up with this funny looking trajectory over here. Okay, so then anyway, so the next setup over here is that now I'm considering a platform that is not frictionless. Okay, so I'm considering a rough platform that's more realistic. So is that if you just really actually go to the playground, right? So if you just stand on this rotating platform, you just stand still, right? So you will really follow the rotation of the platform itself. Okay. So now, so this setup I have, right? So is that I have this person standing on it, right? So and then I just rotate with the platform together like this. Okay. So this time, if you are an observer standing on the ground, okay, so this time you will tell me that this person is rotating, right? So like this. And on the other hand, if you look at the camera setup with the rotating platform, you will say that this person is not moving, right? So this is kind of the opposite to the first case, right? So where you have the at rest at the inertial frame, but then moving at the circular trajectory in the rotating frame. So this time you are moving at the circular trajectory in the inertial frame, but not moving in the rotating frame. Okay, so now let's look at the forces. Okay, so this time we do have a real force. Okay, so that is the friction, right? So if you are actually performing a circular motion, so according to an observer in the fixed frame, so that means that there must be this real force, that is the centripetal force, that gives you the force to do this circular motion. So therefore, this real force would be the mr omega squared, right? So towards the center. Now, if you look at the rotating frame and look for the frictitious force, okay, what you see this time is that there's no Coriolis force. Okay, there's no Coriolis force because in the rotating frame, you don't have any V. Right, so this time Coriolis force is 0. So still you have the centrifugal force. And again, that is intuitive. That is just pointing away. Right, so therefore, in the rotating frame, you do have this centrifugal force. And then you have the centripetal force. And the two forces, right, so effectively cancel each other. And that's why in the rotating frame, right, so you are not moving. Okay. So next, so this time, the person standing on the rotating platform is trying to walk while the rotating platform is rotating. So it's trying to walk on a straight line. So, but by straight line, I mean a straight line in the rotating frame. Okay, so just imagine the following, right? So this is a rotating platform, right? Just imagine that before you set up the experiment, you paint the straight line on the platform like this. It's not spinning now, the platform, okay? And then now the person stand on it, and then now the whole thing start to rotate, and then this person try to follow this green line. Okay. So therefore, right, so he will be walking along a straight line in the rotating frame. Okay. But of course, it won't be a straight line in the inertial frame. Okay. So then this is how it looks like. So in the rotating frame, he or she is walking along this straight line, but then according to the inertial frame, so the path he or she takes is actually like this. Okay. So then let's look at the forces. Okay. So again, I have real force this time, right? So the person walking and that by the friction. Okay. And this time, the Coriolis force is also playing a role, right? So let me draw the Coriolis force. If he or she is walking like this, so then this is the V0 vector. And then again, right, so the omega vector is just pointing out of the page, right? So then what is the omega cross V naught. Right, so the omega cross V naught is to the left, then the minus omega cross V naught is to the right. Right, so this is like this. So that is the Coriolis force is towards the right. So the right means the right hand side of the person. Okay. And now, right, so the centrifugal force is always playing a role, right? So the centrifugal force, again, let me draw that this way, right? So therefore, as you can kind of see that the total fractitious force acted on this person would be pointing like this. Okay. So then if he or she want to walk along this straight line, then the friction has to be pointing like this way, right? Opposite to the sum of the two fractitious forces. Okay. So let me draw this. So the friction, right? So the friction is like this way. So as he or she walk past this O, right? So then you understand that the sign of the direction of the centrifugal force would change, right? So because it has to be always away from the center. Right? Once the position is here, then the centrifugal force is to this side, right? Instead of backward. Now the centrifugal force is forward. Okay. But still, the Coriolis force would be this side. So then, of course, once it happened, of course, the direction of the friction has to be adjusted. Okay, so if the person still want to go along a uniform velocity, so along the way, right? So this person has to keep adjusting the friction. Okay, so in order to balance out the two fractitious forces at all times. Okay. Right, so that the total effective force, okay, so acted on this person in the rotating frame is 0. So constant velocity. So then you kind of understand that why this trajectory looks like this if you look in the inertial frame. So the real force is always kind of pointing to the friction. I mean the friction, the real force is always kind of pointing towards the left hand side, right? So and therefore the trajectory looks like this. Okay, so the last one is that again I have this person walking on the same platform, but now the walking is along the circumference of the platform, not towards the center. Okay. So then, of course, you understand that. So originally, the platform is already doing circular motion. Now he or she just walk along the circumference. Then it just there will be two velocities for this person, right? So and the two velocities need to just add up, right? So the omega, that is the angular velocity, and then plus this V0 divided by R. So that's the total, the angular velocity of the person. And of course, right, so the trajectory would look just like this, right? So in the rotating frame, so the angular velocity is just V0 divided by R, okay, without the omega. So now let's see the forces again, right? So in the inertial frame, so if the person is having this much of angular velocity, angular speed, then therefore the friction must be providing the sufficient amount of centripetal force. Okay, so for that circular motion. So therefore the friction must be given by this mr times, right? So the total angular speed square, right? So towards the point O. So then what about in the rotating frame? So what about the Coriolis force? The Coriolis force. Now, if the velocity vector, right? So the velocity vector like this, right? Then if you do again the cross product, then you find that the Coriolis force is pointing away from the circle, from the O. Okay. And with this amount. And what about the centrifugal force? Hold on, the Coriolis force. Yeah, okay, so the centrifugal force, again, is also pointing away, right? Always pointing away. So then in the rotating frame, okay, so if you try to just combine all the real force and the fictitious force, so what you have? Okay. So then you have the following, right? So the mr, so this real force, so minus the two terms like this. Right. If you expand the first terms, right? So what do we have? Omega square plus 2 omega times V0 divided by R plus V0 divided by R square. So minus 2m V0 omega minus m R omega square. Then you see that this term and this term cancel, right? So this term and this term cancel. Then at the end, you only have this term. Right, so the total effective force in the rotating frame, this one. And that is towards point O, right? So, and that is exactly the mr omega square, right? So the centripetal force for the person to perform circular motion with this angular speed. Okay, so these are all the different scenarios that I try to give you, right? So to understand how the Coriolis force and the centrifugal force behaves in different situations. Okay. Then try to after you go back, we'll try to examine them again. Okay, so one by one. Okay, so to make sure that you understand the differences. Okay. So before we end, so I will just talk about one more example, and that I actually go back to the previous part of the lecture notes. Okay, so this one. So this one is not about rotating platform. Okay, and what I have here is that I have this rigid wire or this rigid rod. Okay, just rotating about this axis, right? So you just imagine that the trajectory of the edge of the rod will look something like this. Okay. And then there's a small feet here that is free to slide, right? So to the left or to the right of this rigid wire. Okay. So that if I just look at the setup from the top, right, so it looks like this, right? So this dashed line is the wire. Okay. I think you might have seen this problem before, right? So, but here I want to solve the problem again, right? So using the fictitious force. Okay. So just to make it more clear, I want to just draw one more picture. Right, so this is the rigid wire, right? So and then this is the speed, the beat, or I just draw it like a ring, right? So it's free to slide, and then the omega vector is pointing out of the page, right? So the whole setup is like doing this rotation here, right? So and then now this one can have a velocity along the wire like this, right? A velocity along the wire like this, and then well, you understand that there must be a reaction force acting on it, right? So the reaction force will be pointing to this direction. Okay. So, and what about the fictitious force? Right. So the fictitious force is that now you know that, right? So first of all, the centrifugal force is easy. You know that it's always away. It's always away from the rotation center. Right. So then this is the centrifugal force. Okay. So then again, what is the Coriolis force? Right. So the Coriolis force would be the omega cross V with the minus sign. Right. So the omega cross V with the minus sign would be pointing to this direction. Okay. So now if you just look at this whole thing, and then because you are in a rotating frame, right? So nothing is rotating. So this rod just stands still. And then if you just look at all the forces acted on this small ring, right? So what do you have, right? So then because this ring is not moving up or down, so then this reaction force must be balanced by this Coriolis force. Okay, and this along the direction of this wire, this rod, then the force that we have would be the centrifugal force. Okay. Right. So now you just need to apply F equals ma. Right. So for the two directions. Right. So for this direction, there's no a. Right. So in the rotating frame. Right. So then you have the Coriolis force has to be equals to the reaction force. And the Coriolis force is the magnitude is 2 times m times omega v, right? So if I just say this is r, right? So the v is actually, right? So the v is actually just r dot. Okay. So therefore, you can see that the magnitude of the Coriolis force over here equals to the magnitude of the reaction force. Okay. Then what about this direction? So this direction, I have acceleration. Right, so in this direction, my acceleration is just m double dot. Right. And that has to be equals to the centrifugal force. Okay. And then I get this first equation over here. Okay. So do you know how to solve this? I think you can solve this, right? So because this m r double dot equals m omega square r, it's just a second order linear ODE, right? So then you should be able to find out that this r is given by some constant times e to the omega t plus some constant times e to the minus omega t, right? So this is not a sinusoidal solution, right? So because I don't have any minus sign over here, right? So what about solving it in the old way that you have learned before, right? So without using the fictitious force, right? So if you still remember, right? So you just use polar coordinates. So what do you have? So without the fictitious force, just use the inertial frame. Then you write down in polar coordinates the two components of the force equals to the radial acceleration and the transverse direction acceleration respectively. Right, so write down something like this: m r double dot minus r theta dot square would be equals to, right? So the radial component of the force, and then the transverse direction. Then you write down this. Right. So before learning about this chapter, this is the two equations that you would write down, right? And this FR, right? So you know that this is 0 because no friction. And then this F theta would be the reaction force. Right. Then, of course, again from this first one, then you get m r double dot equals mr theta dot squared. And theta dot is fixed at omega, like this. Right, so then this equation you get is the same as what you get here. Right. So without using a rotating frame, this is with the rotating frame. Right. So by solving for this R, you can actually go back to find out the reaction force M. Okay, so this is the last thing I want to talk about for today. Okay, so then next time we'll continue.